So, hello student, very good morning to everyone. So, in the last lecture, we have started with the new chapter, that is anti-inflammatory drugs. So, you know that the drug that is used for the treatment of inflammation, that drug is called as anti-inflammatory drugs. And inflammation is defined as a series of changes that occurs in the living tissue following an injury, that is called as inflammation. And it is recognized by the symptoms, that is heat, redness, swelling, pain. Then again, in the last lecture we had learned the types of inflammatory drugs, that is anti-inflammatory drugs. So it classified into two types, that is steroidal anti-inflammatory drugs and non-steroidal anti-inflammatory drugs. So under the class of steroidal, we have learned the example of prednisolone and betamethasone. Then under the class of non-steroidal anti-inflammatory drugs, so it classified into these classes, that is aryl acetic acid derivative, N-anthranilic acid derivative, salicylic acid derivative, aryl propanonic acid derivative, naphthalene acetic acid derivative, organogold compounds, pyrazolone and pyrazolidine derivative. Again, in the last lecture, we had taken the two classes, that is your aryl, your N-anthranilic acid derivative and aryl acetic acid derivative, that is aceclofenac and diclofenac. So this is the example of uh, your N-anthranilic acid derivative, and it is having what it is used in the treatment of osteoarthritis, rheumatoid arthritis, and the side effects are ulceration and hepatotoxicity. So these are the points that we had covered in the last lecture. Next slide. So students, today we are going to learn the synthesis of aceclofenac. Synthesis of aceclofenac. So the synthesis of this aceclofenac start with this 2,6-dichlorophenylamine. This is the structure. The name of this structure is 2,6-dichlorophenyl in presence of oxalyl chloride. So the condensation reaction takes place with oxalyl chloride, and you will get this compound. Then after that, this product undergoes Friedel-Crafts reaction in presence of anhydrous AlCl3. We will get this cyclic product. Then this cyclic product undergoes Wolff-Kishner reduction of this carbonyl group into CH2 by using NH2 COH, that is NH2 COH. So this reagent is called as your Wolff-Kishner reagent for reduction or for the conversion of carbonyl group into CH2. Then the ring opening reaction, the ring opening in presence of NOH, it just open the ring. Then the next step is that this product treated with benzyl bromoacetate, that is sodium diclofenac treated with benzyl bromoacetate, you will get this substituted product. This Br is substituted by this whole group. It's a substitution reaction, nucleophilic substitution reaction. Then the last step is the hydrogenolysis of this bond. Okay, in presence of H2PDC, this bond will break. We'll get this aceclofenac as a final product. Aceclofenac as a final product. So synthesis is very simple. This 2,6-dichlorodiphenylamine is condensed with oxalyl chloride. So you will get this condensed product. Then the next step is it undergoes intramolecular Friedel-Crafts acylation reaction. It undergoes Friedel-Crafts acylation reaction. So you will get this acylated product. Then you will get this compound is called as astatine derivative. Then this astatine derivative is subjected to Wolff-Kishner reduction with hydrazine in alkaline medium. The name of this NH2NO3 is hydrazine in alkaline medium. For alkaline medium, KOH. And when the product is hydrolyzed, you will get diclofenac sodium. So when the after hydrolyze, so this bond will break. In place of NOH, you will get this sodium diclofenac. Then this is condensed with benzyl bromoacetate, and the you will get this benzyl bromo this condensed with the benzyl bromoacetate, and this resulting product is subjected to hydrogenolysis, means breaking of this CO bond, OC bond, and you will get this aceclofenac as a final product. So we'll see the reaction mechanism, how each step, how this first is converted to second, that is its reaction mechanism. So it says step by step explanation of your reaction. So we'll see how the bond formation, bond breaking takes place during the formation of this aceclofenac final product. We'll see reaction mechanism. So for that, how to close this. So let me change the orientation of this page, portrait to landscape. I'm changing the orientation. So our first reagent is 2,6-dichloro diphenylamine. So it's having this, first I have to write here, and it react with your oxalyl chloride. It oxygen, chlorine, nitrogen, and on nitrogen there will be a positive charge, because now nitrogen having 4 bonds, so there will be the positive charge 1 2 3 4. So there will be positive charge on this nitrogen. Hydrogen. Then single bond, C double bond O, and here the Cl. This is your Cl, here carbon, this Cl, and this is also your Cl minus. Now the next step, what happens, this Cl minus takes this hydrogen, it takes this hydrogen. So let me show you how it takes that hydrogen. So I have to copy this, Control C, Control V. So here this oxygen will form double bond here, Cl will not there here, oxygen double bond. Now it's correct. Now this Cl minus, in the next step this Cl minus takes this hydrogen. So Cl is a leaving group. So in the next step this Cl minus takes this hydrogen and it taking that hydrogen from this quaternary nitrogen to stabilize that nitrogen. So it will take this hydrogen and it stabilize this nitrogen and HCl is a byproduct. HCl is a byproduct. HCl is a byproduct. So one arrow minus carbon is there. Now the next step is intramolecular Friedel-Crafts acylation reaction. Intramolecular Friedel-Crafts acylation reaction. So this double bond of this aromatic ring will attack on the carbonyl carbon because this due to this nitrogen atom this ring will act as a nucleophile, and in FYBSc you have learned that electrophilic aromatic substitution reaction. So in that the ring act as a nucleophile. So here this double bond will attack on carbonyl carbon of this your oxygen chloride. Intramolecular Friedel-Crafts acylation reaction takes place. This bond will break and the bond pair shift on oxygen. So now this carbon loses its electron, so there will be the positive charge on this. There will be the positive charge on this carbon. So the next structure will look like this. Now on arrow and Friedel-Crafts anhydrous, AN for anhydrous, ACl3 anhydrous, Cl oxygen will be there, then bond Cl and this is your hydrogen. Now in the next step is this negative charge will delocalize. This oxygen have a negative charge, so this will delocalize here, okay, and Cl will be the leaving group. Cl will be the leaving group. So this after delocalization of this oxygen anion, it form carbon oxygen double bond. Then once it form the carbon oxygen double bond, this Cl will be the leaving group and you will get C double bond O. Then in the next step, so the next step here is your minus Cl because Cl is a leaving group. So minus here is T9. It's a astatine derivative. Now this astatine derivative undergoes the reduction of this carbonyl group into CH2. The reduction of this C double bond O into CH2 by using reagent, and the name of that reagent is Wolff-Kishner reduction. It is one of the name reaction, and the name of that reaction is Wolff-Kishner reduction. Wolff-Kishner to NH2 NH2, 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 and KOH, that is hydrazine. This NH2 is called as hydrazine in alkaline H2 in presence of oxygen, and there will be the negative charge on that oxygen. So negative charge. Now here is your nitrogen, 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 nitrogen having two hydrogen. So nitrogen, and on this nitrogen there will be a positive charge. So let's to erase this, so the negative charge will be here. Now this nitrogen having two hydrogen, 1, 2. So just add here hydrogen and positive charge on this nitrogen, positive charge, positive charge on this nitrogen. And the next step, what happen, uh, your so you are using base. So the next step, it's a simply dehydration reaction. So you are using base, that is KOH, KOH, and the role of this base is it abstract hydrogen. Now the next step, what happen? This negative charge, this OH minus takes this hydrogen from this nitrogen. So you are using the base. So the role of this base is it takes this hydrogen, and the bond pair will shift here to form carbon nitrogen double bond, and this OH is a leaving group. So this finally it's a water is a leaving group. It takes this hydrogen convert to OH, and overall the water is your leaving group. So the next structure, there will be double bond between your carbon and nitrogen. Now this group will not be there in the next structure. So, and there is a double bond between this carbon and nitrogen. So double bond is there. So it takes this OH minus take this hydrogen proton, and the bond pair shift here. It form the carbon nitrogen double bond, and OH is a leaving group. So OH is a leaving group. It forms this carbon nitrogen double bond. Now in the next step, your this OH minus convert to water molecule. So oxygen here. Hmm. There will not be, so to erase this because it is in the next step. Just to erase this. Hmm. So in the next structure, there is a double bond between this these two nitrogen. So double bond will be there between these two nitrogen, and there will be the single bond between this carbon and nitrogen, and there is a negative charge on this carbon, negative charge on this carbon. Now this is carbanion. This carbanion takes the hydrogen from water molecule. So in the next step, it taking hydrogen from water molecule. So in this step, you know that this OH minus take this hydrogen and convert to water molecule. Okay, so it converts hydrogen, hydrogen. Now, on the next step is simply it's say now the next step, this OH minus can, once this carbon and take this hydrogen, you will get this, so into is a leaving group. So this OH minus takes this hydrogen, and there is already carbon nitrogen double bond, so when this OH minus take this hydrogen, the bond pair will shift here and it will form carbon nitrogen double bond. And after forming this nitrogen double bond, this carbon nitrogen bond will break and the bond pair shift on oxygen. So there will be the generation of carbanion, and negative charge species will generate, that is called as carbanion. So we will get this carbanion. So I will show you. You will get this carbanion. So there is a negative charge on this carbon. Now next step is this OH minus take this hydrogen, it convert to water molecule. It will convert to water molecule. So this carbanion takes proton from that water molecule. So the next step, it takes that one hydrogen from that water molecule. So this is your carbanion, and this carbanion take this hydrogen, convert to CH2, convert to CH2. So it convert to CH2. So negative charge will not be there in the next structure, because after taking this proton, there is a that carbon will form bond with this hydrogen, and a nitrogen. This is so your C double bond O, OH group. Now the next step, now the nitrogen have a negative charge. This N minus take this hydrogen, and it will convert to NH, and there will be the negative charge on this nitrogen. Sorry, there will be negative charge on this your oxygen. So it takes this hydrogen from that hydroxy group, and it will convert to NH. There is a negative charge on this oxygen. Negative charge on Br, Br, then C, double bond CH. So yeah, the bond will be there. C6 oxygen here. So in the next step, this is your benzyl bromoacetate. So it will react with this benzyl bromoacetate. So this OH minus will attack on this CH2, because this CH2 is electrophilic in nature, because that carbon is electrophilic due to presence of this electron withdrawing group, carbonyl group, and this bromine, both are electronegative. So that carbon will act as a electro that carbon is electron deficient, electropositive. So this OH minus will attack on this CH2. So OH minus will attack on the CH2, and your Br is a leaving group. So finally this now this there will be this counter ion with this oxygen. Na will be there with this OH minus. So the leaving group will be minus NaBr. This Na, then this OH minus attack on this CH2. Br is a leaving group, minus NaBr. Then this OH minus form bond with this carbon CH2, and the final product will be like this. I will show you that final product. So this oxygen will join to this CH2. So oxygen single bond CO, H2, CH2, H5, C6, H5. So this is your final product after reacting with this uh, benzyl bromoacetate. Then the next step is next step, and it's the last step. In the last step, this product will react with your C. So the role of this reagent is what it used for the breaking of carbon oxygen bond. So it breaks the bond from here. So one hydrogen here you are using this two hydrogen, so one hydrogen will join to support to this oxygen and one will join to this CH2. So this toluene will be the one product will be toluene and one will be the your aceclofenac. So after reacting with this, you will get the final product, that is C6 plus. This is your Aceclofenac O, say simply O. Then the next step, that this OH minus ion, then this leaving group takes the hydrogen, convert to H2O, then bond pair will delocalize, it form nitrogen nitrogen double bond. This double bond, this bond will delocalize and the bond pair shift on carbon. So there will be the negative charge on that, and that negative charge takes hydrogen from that this water molecule which is generated here, and it convert to CH. So there will be the bond between carbon and hydrogen. So this carbon takes this hydrogen, so there will be the formation of bond between carbon and hydrogen. Then the next step, so once this takes this hydrogen, it convert to OH minus. So this OH in the next step, this OH minus will use. So this OH minus takes this hydrogen from this nitrogen, and the bond pair will delocalize here to form carbon nitrogen triple bond, and N2 molecular nitrogen is your leaving group, and this bond pair will delocalize, this bond will break and the bond pair delocalize on carbon. So there will be the negative charge on that carbon. Then that carbanion takes hydrogen from water molecule. So this here the water will generate. So this OH minus takes hydrogen, convert to H2O. So this in the next step, this water will use. So this OH minus takes this hydrogen, convert to CH2. Next step is simply the ring opening reaction. This NaOH will attack on this, and it will open this 5-membered ring, and there will be a negative charge on this nitrogen. It takes hydrogen from this OH group of your carboxylic acid and convert to NH. In the next step, this OH minus will attack on the benzyl bromoacetate, because this carbon is electropositive and Br is your leaving group. And so here what this nitrogen is oxygen will not be alone here. The O minus and Na plus, the sodium will be attached to this oxygen anion. So minus NaBr is leaving group, and you will get this final O substituted product, because oxygen will form the bond with this carbon, so bond with this CH2. So O CH2 C double bond O CH2 C6H5. The next step is hydrogenolysis, breaking of this bond. From here it will convert to CH3 C6H5 and CH2COH. So the hydrogenolysis reagent is H2PDC, and you will get your final product, and the name of this final product is aceclofenac, and this is your toluene as a byproduct. So this is all about the reaction mechanism. Thank you.